Hi, everyone. I'm super excited to talk to you today about our techniques that we've been looking at for deep learning and body pose estimation for VR and AR. So I first of all want to start with a small disclaimer. This was very much work that was doing and undertaken as a pathfinding exercise. And so what I'll show you is some prototype hardware, some research, and it extended over the course of 6 to 9 months. The work that is being covered isn't productized, and I have to warn you, there is excessive use of programming art. So if we've got any art critics in here, really close your eyes. There's also some technical cheats that we're doing to make machine learning very efficient, and I'll go into more detail about those, but really they're actually great advantage that should be taken, and I'll talk more about them as we get into the talk. So to give you a little bit of overview, and I mean, there is a lot to cover, so really I'll race through this. We'll be talking about the motivation behind this work, the related work in both body and hand tracking, an overview of the framework that we're looking to employ, as well as the need for real training data. We will also look at the use of a multi-view capture system, the machine learning part of our approach, model optimization for refining our estimates of the skeleton, inverse kinematics and the application of that to our estimates, as well as an application demo. Finally, wrapping up with conclusion, and then food and drinks. So really the motivation behind this work is that regardless of whether you're working in VR, AR, XR, or in mobile augmented reality, it's really a core problem that we need to understand more about humans and human tracking. When we think about computers, we know that regardless of technology's advances or slowdowns, that really there's going to be two constants, both humans and computers. And so any work that we do towards human understanding is going to benefit a range of applications. In particularly, this talk looks at VR and AR as its core applications, and that's where we'll be able to apply the cheating method that I mentioned for machine learning. So a little bit about prior art and the related work. I'll first of all talk about RGB-based body tracking and mention some very notable works in this space. So in 2017, OpenPose was released, which is a machine learning architecture using convolutional neural networks for regressing and estimating the position of all of the body's joints. And this is capable of running for multiple people with great accuracy and is a general purpose algorithm for finding the body. There is, however, some drawbacks in such a system. In particular, the frame rate of this is limited to around 6 to 12 FPS, at least at the time of this publication. And this is attributed to the size of the network and the fact that you have to run such methods on dedicated or heavily parallelized compute. And we can see that here this architecture has actually multiple stages as the last portion of its network. And so this actually in the paper can go up to, I believe, 6 iterations of that final stage of the network. Around a similar time, we also have hourglass networks. Again, these offer great accuracy and a general purpose solution for body tracking. Again, these are GPU-based method and are very deep in their architecture. Each one of these hourglasses is itself a complex convolutional neural network going from appearance image through to a heat map image to estimate the position of each of the parts, stacked one after another, giving us a total architecture. And finally, we have dense pose, which is offering a surface representation of the body. And this is great for if we want to do texture painting onto a person or understanding the contour and the way the body moves, rather than just the underlying joint positions. Again, it's a general purpose solution, and so it has to contend with challenging lighting conditions such as this picnic scene. And in order to train this technique, they actually had to annotate 5 million ground truth points on 50,000 images of people. So it's pretty clear that deeper networks is the direction of this type of work, and general algorithms require a lot of compute, impacting their potential for devices such as standalone headsets. And ideally, we don't want to be going towards a headset that looks like this. So I'll talk more about depth-based methods and their benefits. So really, there have been two main techniques used for hand tracking. The first is machine learning and also body tracking. Using data, you can train things like randomized decision forests to identify the parts of the body or the parts of the hand. And these can provide a per-frame estimate of the position of the joints. They offer a great frame rate, but often require millions of images to be able to capture all of the variety of the hand or the body. And so there's an alternative approach where we look at model fitting, where you take a priorly built model of a hand or a body and use techniques such as signed distance transform function to move it towards the point cloud data that we get. And I'll go into more detail about point cloud data, but basically we take a model and we make it look like what a person or hand would look like to make that data. And what's nice about these techniques is they implicitly enforce kinematics. There's information and understanding about the shape of the hand or body, but they do require multiple simulations. So this brings me on to hybrid approaches. Hybrid approaches look at combining both machine learning and model fitting. So it was actually back in 2015, around 2016, where I had been looking at hybrid approaches for hand tracking, where we used a randomized decision forest to localize the parts of the hand and then fit them to a model. And since then, double fusion came through at CVPR by Yu et al. For estimating the pose and surface of a person. But these are both still very computationally demanding techniques. And from my prior work, I was under the impression that you could do very good work with very limited compute. So in fact, I wrote an algorithm that was working on hand tracking that would run on a CPU alone at 40 frames per second using this hybrid method that I mentioned. So as I've mentioned, we'll be talking about machine learning in agreement with point cloud fitting to give us our skeleton tracking. But we're also going to exploit the HMD's position as well as the controllers. And this is what I meant by cheating. We effectively use prior knowledge from these known positions to give us very stable positions of the user and then constrain our learning problem. So the full pipeline is rather extensive, and we have to look at both the capturing of data as well as the training framework through to then our inference and real-time aspects. So across the top, we look at calibration and capture of a multi-view system, the data labeling process, rectification of that data so that it's suitable for learning from, and then real-time estimation is on the bottom where we do the capsule fitting and machine learning. And so for the real-time portion, we take a person in a known space. We pass their images through a convolutional neural network that's very small, alongside the information that's coming from the controller's headset and controllers, and then regress a heat map position for each of the joints, as well as a floating point value for these key points of the controller and the headset. So I'll go into a little bit more detail about the need for real data. So I understand that some of you may not be familiar with depth data. And so I want to introduce you to what depth data looks like from one of our cameras. We collect both color, which is RGB, as well as a distance from the camera, which is our corresponding depth. And so every pixel has a corresponding depth value. And with the knowledge of our intrinsic calibration, we can also produce a point cloud, where every sample is representative of a point on the front surface of a person. So you effectively get this front shell. So you could use synthetic data for training machine learning, but often it's very clean data, and so we would see that there's artifacts and characteristic traits of real data that isn't missing from a synthetic system, and it's very difficult to reproduce accurately. So we can collect real data, and more often than not, you'd have to annotate it. But clicking through millions of images is very time-consuming, and it's costly, it's inaccurate, and it's super boring. I mean, like through my PhD, I did a lot of manual annotation, and I can tell you, like, it's a real painful experience. So we look at alleviating that with multi-view capture. And this was really inspired by the great work that's been happening at the CMU Panoptic Studio, where they take a 2D estimator of the position of the hand and then project that through to a 3D position and reproject that back to 2D and iteratively refine their estimates for the position of all of the hand's joints. Doing this, they also made a body tracker, and you've seen OpenPose already. Well, we actually use OpenPose to annotate 2D images that come from our camera. And we actually built a small prototype system to validate the triangulation code, where you can see here the view from me of the rear, as well as the frontal view of me. And this here is an example of the annotation that you get from just 2 viewpoints. It's terrible. It's really noisy. It drops out. And so with more viewpoints, we actually get much better data. So we look at doing so with many more cameras, or more cameras. So we want to time sync these cameras and calibrate them all into a single coordinate space. So hardware synchronization is really the way to go for this. You can do software synchronization for triangulation, and we use that actually for our annotation for a large portion of our data. But we found that if we wanted to do more complex things like volumetric reconstruction, we really need to move towards hardware synchronization. Otherwise, you start to see things like those ghost artifacts around the arm. And we actually have a white paper out now where you can go ahead and use our cameras with hardware synchronization in your own lab. So as I mentioned, we wanted to go up from 2 cameras to 6 cameras. Now, I said many more, but this scales quite nicely. You can go to many more cameras and have a dedicated capture node for each camera. So with our 6 cameras, all positioned at 60-degree intervals, we had a nice multi-view system that allowed us to collect data. But we also had to calibrate them and bring them all into a unified coordinate frame. And we did so using a Vive tracker. So I don't know if you're all familiar with Vive systems, but it's available. You can get a hold of these pucks, which give you a 6-DoF pose in 3 space. and we actually attached one of these onto a calibration chart. And we were able to then calibrate both our camera system as well as the Vive system. And you can see here, moving the board around, we'd established the position of each of the cameras in turn, and we could then actually, in an offline process, refine them even further to give us better accuracy. And about now, we should get the 6th camera. Oh, maybe they're all there. Anyway, this is the resulting calibrated view. And so this marks the result of really 2 main tools that we needed to have, the multi-camera calibration and the synchronized data capture. So we now look at the automatic annotation, which we get when we combine the 6 viewpoints. You can see here that we're able to resolve all of the joints much more consistently. There's some dropout with my face, but I am wearing a headset. And you can see subtle motion, like raising my leg, shrugging my shoulders, or even jumping in the air. And all of this data is being annotated automatically. So I didn't need to click on any images. I didn't need to outsource any laborious tasks. It's great. And we captured many, many, many examples of this type of data. In fact, we filled all of our hard drives in our capture nodes. We had to buy new hardware in. It was a telling time, but really it was worth it because we were able to then capture great amounts of variation in the body and the human pose. So we now look at the data rectification process. We actually have now a virtual human, so to speak, and we can render them from any viewpoint that we want to. And so we actually take an orthographic reprojection, so that's basically drawing a cube around the person and rendering it down to images from different angles. The idea being that when we come to train a machine learning technique, that we can effectively rule out camera pose as one of the variances that we have to cater for. And this is exactly the way that we cheat our machine learning process. So again, this is that same sequence now being used to render out 6 viewpoints. And we can actually merge point clouds together to give us even more dense data. So you see that all of the annotation for that shrugging of the shoulders, jumping up in the air. I even do a little ski jump. And of course, things crash, but that's fine. And not always things perfect, so we have to look at how we can rule out examples where the annotations failed. And we do so by actually using a pretty strong constraint where people don't tend to grow very quickly. And over the course of a single sequence, their bone lengths don't change. So we can actually use statistics to simply rule out examples that don't fit with our understanding of how the person's proportions are. We also found that for the majority of data that we collected, people are just kind of stood there like this. And so we actually have to resample our data to reduce it down to a uniformly distributed sample set so that we can really get the most out of our learning. So you see here, we actually take an estimate of the density of all of our data and then resample it so that it's nicely uniformly spread out. So again, I'll mention the advantages of such a system. Really, no manual annotation, and for a small team, that's really important. We could train other cameras if we wanted to. We could bring in a new camera that we were working on, put it into the same system, and suddenly we'd be collecting new data for it as well. Using the Vive system, we'd get all of the nice, really clean data about the headset position and the controllers. And with just 30 minutes of capture, we were able to get 50,000 fully annotated training samples. So I'll talk about our network now. So really, we want to be able to provide a single camera solution. This is great for the end user because they don't need to have 6 cameras in their living room if they want to play VR. So from this slide onwards, we're going to talk about only using one camera. But we've taken now all of our training data from many viewpoints. And we developed a tiny network. This network literally has, I believe, 6 layers, mostly convolutional, bringing the image down to a very compact representation where we add in the information about the controller and headset position. We then explode it back out to give us an estimate for the heat maps and the position of all of the joints inside of each image, as well as the original estimate for the controller and headset position. And this is the result of our network. By providing headset and hands positions, we're able to even work outside of the camera frustum. So you'll see at times where my colleague actually reaches outside of the camera, and because the controller is giving us lots of information, we're even still able to track the the elbow and the shoulder. Another nice fact is that we've got the ground plane there telling us where the person is in relation to the ground. So if they jump up, then we can build associations with the fact that the feet have left the ground. So I mentioned we're talking about a hybrid solution. This has covered the machine learning portion, and now we'll talk about model optimization, where we effectively bring a model in line with our point cloud data. In this case, we're doing it with a cuboid, very simple. And it's a little bit more complicated if we're going to talk about articulated body parts. In essence, what we're doing is finding an assignment that is nearest neighbor, so every part to its closest parts of the point cloud, and then understanding how those points influence that portion of the model. We then optimize the skeleton position in an information-rich environment. So it's now already established all of the impact of parts to point cloud to then be able to derive the whole skeleton. So in essence, we basically have capsules or these cuboids attached to the point cloud, and then they're solved using GPU or some parallel architecture. And then we solve the joint constraints in CPU, where there's not so many. So here you can see the orange points are the point cloud data coming from our camera, and the capsules that are then being attached to the point cloud. And you can see the accuracy is somewhat limited, and it often becomes trapped in local minima. I suggest you don't try this in real life. So this is where the machine learning part really comes into play. Now assisting the capsule fitting with machine learning, tracking is much more stable. And you can see that my colleague's legs are being estimated really well, even though that they're close together. His hands are pretty stable. We aren't really attaching the controllers at this stage, but we do so later on. And you can see here he's able to wiggle his feet, give a little wave, a bigger wave, even fight. So this gives you an opportunity to see what he's doing in the infrared spectrum. Head tracking comes for free, basically, from the HMD. Torso tracking comes from our model fit and machine learning, of the hips, really. So you can play hula hoop in this space. and we've got legs and feet. So you can kick a ball or step over things. You can even run in VR, where before you might have had to use a puck controller. And if you're Scottish, you can do a little Highland jig as well. So you can see when we compare it to conventional tracking methods, we're able to deal with really complex and quite intricate motion where normally body parts slide around, they jump between different positions. There's a lot of noise in conventional methods. Whereas we get very stable tracking due to the model estimate. So until now, we've not really been applying any kind of inverse kinematics or kinematic constraints. This means that we're able to optimize much more efficiently, and we can apply the IK after the fact. So we wrote a Unity plugin, which would allow us to take our model estimate and put it into a game. Final IK offered a off-the-shelf solution for inverse kinematics, and we used it to actually attach a character to the pose estimates that we were having. And so we're ready to go. You can see here in this demo application the ability to play with a ball pit, which you would never have been able to do without puck controllers or many cameras. You can even look at the side of your foot. You can scoop at the balls. You can get right in amongst them. The only problem is that it's really difficult to pick up a ball with two controllers. So it's a little frustrating at this stage, but that could be improved with better application development. One nice thing is that we've also able to track the elbow position, which you can't do with a controller only. And so you get all of that detail with the inflection of the wrist. So in summary, we've presented a tiny convolutional neural network for joint inference, optimized and is used in confluence with optimization that's written in an efficient LM solver, so Levenberg Marquardt. We use real data to train, providing us with, so we use real depth data. So that actually provides us with invariance to lighting conditions, to texture invariance. So we don't need to have a person come in with a red t-shirt, a blue t-shirt. We synthesize a new viewing frustum for our training data, and this actually gives us camera pose invariance. And so we're actually taking out of machine learning a lot of the problems that make it difficult. We also show a roadmap for creating a lower cost, multi-view, panoptic capture stage with depth and Vive system. And so thank you very much for your attention. It's been a real pleasure showing you our months of work. Thank you again.